Hello, everybody. Greetings. Welcome to Unit 2. And that's the unit on the solar system. This is big stuff. We're going to talk about how the planets work. We're going to talk about their moons, the origin of these bodies, and also the small bodies. So it's all over the place. We're going to start off with chapter 15, where we talk about the origin of the solar system and extrasolar planets. Presumably, they all originated in general basically the same way. The text has some interesting aspects of this that you don't normally see in a text like this, which I like. The first is this one right here. They outline a theory for the origin of the solar system, but they also talk about the origin of the atoms in your body, which is a very interesting topic. Yeah, and I want to talk about it in general. We'll fill this picture in as we move along in the course. But here's the deal. If you're wondering where the elements in your body came from, first of all, we know that hydrogen and helium came from originally from the Big Bang. That's the origin of the universe about 14 billion years ago. Okay, so almost nothing else did. There was certainly no heavy elements of the type in your body that your body needs to exist. There were no heavy elements like silicon and iron that are needed for a planet like the Earth to exist. So none of this stuff existed. There weren't any people around shortly after the Big Bang, believe me. The heavy elements, namely things like carbon, oxygen, phosphorus, nitrogen, just goes on and on and on. All of these things were created in stars, as a matter of fact. Heavy elements from earlier stars. Stars go through a process, particularly the big ones, go through a process where they're producing all the heavy elements ultimately in the periodic table of elements for chemists. And so that was demonstrated sort of post-World War II. It's been known for a long time. And it's an extraordinary story. We're going to put that off till we get to star stuff. But anyway, now you know where all the heavy elements came from. The question is, those heavy elements were produced in big stars, stars that were 8 times the mass of our sun or bigger, okay, sometimes 20 or even 30 times the solar mass. And so the heavy elements, which are absolutely essential for complex forms of life, didn't exist until stars produced them. Fortunately, it didn't take long. Then the question is, how do those heavy elements get out of those stars and into the clouds, which lead to planets like the Earth? And the answer is they get blown apart. These big stars become what are known as supernovas. You need to know that word. That's just a big star above 8 solar masses that explodes late in its life, and it throws out these heavy elements that it's picked up since before it existed from the cloud that collapsed to it, and throws them out into space and hits smaller or bigger clouds, doesn't matter which, that happen to be in the vicinity. And it does two things. It seeds those clouds with heavy elements, which are needed for, remember, Earth-like planets and you and me. And it also gives these clouds a pretty nasty nudge. They get pounded. And generally, that's what these clouds need. They need a nudge to start collapsing into stars and planets. We'll talk more about that in this star section. Anyway, here's the solar nebula theory. This is an evolutionary theory. In other words, it's something that can happen anywhere in the galaxy. It doesn't require unusual events like, say, close approaches of nearby stars. Wherever there's a gas cloud, something like this could exist. Anyway, the solar nebula theory says that the sun and the planets ultimately condensed from a spinning interstellar cloud of gas and dust. Remember, in this story, the gas is hydrogen and the dust is silicate dust, just like the dust you see around in your everyday life. What determines whether these clouds are generally several light years across? They're big, much bigger than a solar system. So they have to collapse and get hot, and there's a battle between gravity, which is always trying to pull things in, and gas pressure, which is always trying to push things apart. And if the cloud is just right, and if it got popped pretty good by the supernova, it will collapse into something that will develop into a solar system. In a nutshell, that's how the theory reads. Here's a survey of the solar system so that we can see what it is that makes people believe this story might be true. First of all, everything is spinning and moving in the same direction. The planets and the sun spin in orbit in the same direction. There are exceptions, but not many. Things like Venus spins backwards. That's probably due to something that happened to it early in its history. Everything else, though, looks pretty much the same. Take a look at page 345. There's a table there that'll make a list for you. It's a pretty persuasive list, frankly, when you really look at it. The other thing is there are two types of planets, terrestrial and Jovian. Terrestrial are rocky planets like the Earth. Jovians are gas planets, mostly hydrogen and helium, and a few other things like Jupiter. And the other interesting thing about this is that it's warm early in the solar system's history. The sun keeps things warm close to it, not surprisingly, and it cools off far away. So the question is, how did water ever get to the inner planets like the Earth? And the answer is, it was delivered later by asteroids and comets, although it's not exactly known how that worked. But it had to come later because, well, in the case of the Earth, you'll see, when the moon originated, it originated from a collision which hit the Earth and blew away the atmosphere, okay, and the oceans. And so that needed to be replaced. And that's one of the things that replaced it was collisions later by asteroids and comets. The small bodies, asteroids, comets, Kuiper Belt objects, meteors, all were a byproduct of this planetary origin theory that we're talking about. We know that the solar system originated about 4.6 billion years ago. We have actual radioactive dates on this from the moon that indicate the oldest parts of the moon are 4.6 billion years. We believe this is a good thing to follow away, that the solar system originated all at once. Okay, so there isn't a sequence of events. Most everything is around 4.6 billion years old. Now, here's the final touches for planets in this business. Accretion and differentiation, you need to know what those things are. Accretion is just simply going from dust to larger particles, and that's what this is showing. When you have an area filled with dust, it starts to condense and collect, and pretty soon you've got large areas with large clumps of dust. And these eventually, over time, turn to solid particles. The solid particles collide. That's what's known as accretion. That's all there is to it. And then eventually you wind up with several large particles as a result of accretion that have pretty much cleaned up their orbit paths. This will come up a little bit later when we talk about this downstream. Differentiation, even more simpler. Most of the planets probably formed with uniform compositions. It's like being well mixed. It's like when you put say you're baking a cake and you put the eggs in and the other stuff and the milk, and then you stir it up and make it well mixed. That's the way planets were originally. And we know that the Earth and other planets, we know the Earth for sure has a large iron core, which wasn't there when it originated. So the way you differentiate a planet that's really big like this is when it gets hot, it melts. And all the heavy stuff, which is iron, falls to the center. And the lighter stuff, which is the rocky stuff, winds up floating to the top. So now you've got two processes here that you need to be aware of. Accretion, that's where dust turns into small particles, which winds up through collisions, turning into larger bodies which become planets. Eventually, their gravity starts to help in this process. And you've got differentiation where heating of the interior, I haven't told you why it's hot yet, results in an iron core and a solid silicate mantle. Sorry. Okay, this is, we're actually almost done for this thing right now. The extrasolar planets are a fascinating area today. There are thousands of them, well over 3,000 extrasolar planets. These are simply planets that are around other stars, okay? And of course, we see the ones best that are closest to us, but the belief is they're all over the galaxy. There may be, some people suggest that there are billions of planets, not Earth-like planets, just planets all over the place. Now, I chose this slide because it's simple, but it allows me to point out the things we do see. These things are all over the sky, by the way. And here we're actually showing you separate stars without names. Actually, the names are right here. 51 Pegasi here, 55 Cancer, 70 Virginis, and HD. Notice there aren't any Greek letters here. This is a different sort of catalog than we've talked about before. Anyway, this is the distance from the star, and we've actually showing the distance of the Earth, of the solar system planets. And the 47 Ursa Majoris has a large, this is called a super Jupiter, 2.4 times the Jupiter mass, way out here beyond Mars. In fact, this one is not that far from where Jupiter is, but the rest of them are very anomalous. 51 Pegasi. Notice this is a 0.6 Jupiter mass, still a very big object that's almost sitting on top of its sun. This one is 0.8 from 55 Cancer, almost as close. Notice they're well inside Mercury. These are called hot Jupiters, by the way, because, and notice here's one 6.6 at 70 Virginis, and here's another one that's 10. There are lots of these super big planets. They're called hot Jupiters because everybody knows you can't create a planet like this close to a star. It just cannot be done. These things were created way out here in the outer solar system. You may remember that Jupiter is like 5 AUs from the sun currently. Today the Earth is 1 AU. That's an astronomical unit. And so these things must have originated way out here, and then somehow they migrated in toward the star. Exactly how that worked is still a bone of contention, but it does seem likely that if you had a big object like this, 6.6 mass Jupiter object, migrating in, any planets like Venus or the Earth would have been tossed out of the solar system without any doubt. So this is both interesting news and bad news because it shows us that these big planets exist all over the place, but it also suggests they weren't born here. They were born out here in the suburbs, and they came in and basically cleared the inner solar system. So it's kind of a mixed thing.